Okay, welcome to this video. Today we're going to be looking at a proof of the fundamental theorem of calculus part 2 that comes from the book Principles of Mathematical Analysis by Walter Rudin, also known as Baby Rudin. So the fundamental theorem of calculus, and we're calling this one part 2. Okay, so this is a very nice proof. It's a very nice theorem. It's a wonderful theorem. I really also love both the proofs of the fundamental theorem of calculus part 1 and part 2 that are in the James Stewart calculus book. I think they're amazingly beautiful, and they bring in together all of the theorems that the students have been studying up until then. So well, a lot of them. It's very nice anyways. So let's get started with this proof. And here's what the theorem says. It says if we have a function f that is Riemann integrable on an interval from a to b, closed interval, and if there is a function that's differentiable, so if there is a differentiable function, we're going to call it big F on this same interval with the property that, so such that if I take the derivative of this big function, or if this function big F, it's going to be equal to little f, then our conclusion is that the Riemann integral from a to b for this function little f is equal to the big function f evaluated at b minus the big function f evaluated at a. Okay, so we're going to prove this using partitions and using theorems about the Riemann-Stieltjes integral. So the first thing you want to note is that if a function is Riemann integrable, well, let me say it like this. The Riemann-Stieltjes integral contains the set of Riemann integrable functions. So in other words, the Riemann integral is a special case of the Riemann-Stieltjes integral. And we're going to use the fact that if you have a Riemann-Stieltjes integrable function on an interval from a to b, then we can find some partition and an epsilon such that the upper sum minus the lower sum of the Riemann integral with the function in that partition is less than epsilon. So let me write that down because maybe it will be more clear. Okay, so here's our theorem. We're going to make use of every piece of this theorem here in our proof. So first we're going to start by saying this. First thing you want to say, okay, proof. We're going to say let epsilon be greater than 0 be given. Epsilon greater than 0 be given. Then we're going to choose some partition, our partition P. That looks like an R, doesn't it? Partition P that looks like this, x sub 0 or x naught, x1, x2 up to x sub n. That's on a to b, and here, you know, x naught is a and x sub n is b. Okay, so we're going to let epsilon be given, then choose a partition P with this form such that if we take the upper sum of this function in this partition minus the lower sum, the lower Riemann sum, it will be less than epsilon. And the reason we can do this is, so this is what we want to show, right? We want to show that we can find an epsilon so that this difference here will be equal to this one. So in other words, This that's what this says, because this epsilon is arbitrary. These two things end up being equal since f is Riemann integrable. Okay, and because f is Riemann integrable, well, the set of Riemann integrable functions is a subset of the set of Riemann-Stieltjes integrable functions. And so that theorem that says if your function f is Riemann-Stieltjes integrable on an interval from a to b, you can find a partition for an arbitrary epsilon such that the upper Riemann-Stieltjes sum minus the lower one is less than epsilon. Epsilon is arbitrary, that means they're equal. Okay, so we're going to use this theorem from Riemann-Stieltjes integrals, and because the Riemann integral is just a special case of that, we can apply that here. Okay, so this is what we want to do. So we choose our partition, right? And now we're going to say the following. So we've chosen a partition P. We've made use of this part of the proof. F is in the set of Riemann integrable functions. Okay, so now we're going to make use of this part. It says there's a differentiable function f in a to b. So we're going to use this now. We're going to say something about the differentiability of this function. We're going to say this. The mean value theorem gives for, so we're going to say some ti in a subset of our partition, which is going to be x sub I minus x sub I minus 1. So this x sub I minus x sub I minus 1 is in AB. It's between A and B. Okay, and then ti is in there. So what does it give? It gives us gives for so let me see if I can write this correctly. So the mean value theorem gives for some ti in this interval. We can write down this. We can say capital F of x sub I minus capital F of x sub I minus 1 is equal to this derivative times x sub I minus x sub I minus 1. Okay, and really we've like made a pretty big step in the proof right here with this statement. Okay, so now we've got, and this is because of the mean value theorem. So now, hold on. Let me mute this while this vehicle goes by. Yes, I'm in Thailand, and they often have vehicles with very loud messages or things playing, drive around the neighborhood, whether it's for an election or for like a sale at a mall, something like that. So anyways, sorry about that. So let's continue with the proof here. So this is a pretty important statement here, and we're going to use this now, and the fact that our condition says that capital F prime is equal to little f. Okay, and what I'm going to say is this now. Well, this guy right here is equal to little f of t sub I. And well, what is this x sub I minus x sub I minus 1? That is simply delta x sub I. Okay, so we've got that these two things are equal. Well, actually, these three things are equal, but in particular, this one and this one. And so what I can get from this is I can say, so the sum from I equals 1 to n of this guy, this product, is equal to the sum from I equals 1 to n of f of x sub I minus f of x sub I minus 1. Okay, and now we're narrowing it down here, because what exactly does this thing equal? Well, if you think about the fact that if I were to write this all out, I would get all of the terms would have their opposites present and would be adding these terms to their opposites, except for the first one and the last one, because they're off by one. Like this one is one less than the other one. So what does that mean? So if you don't believe me, I think you should, take a moment and try to write it all out. If you write down f of x1, you're going to have, first you'd have f of x naught, which would be f of a. Then you would have f of x sub 1, but you would have minus f of x sub 1. So if you understand this already, you're probably like, shut up, I get it. But just remember, there's other people who don't get it. So, so everything will cancel out except for the first term and the last one, like this. And that, my friends, is exactly where we want to go. But we're not quite finished. Now, if we were doing this proof in calculus, we'd be finished. But we're not. We have to prove that this difference minus the Riemann integral for f on a to b is less than some arbitrary epsilon. So what can we do? How can we do it? Okay. So then we can write down this, and I'm going to do this little trick here by a previous theorem. Don't be mad. So there's not a whole lot of mystery here, but by previous theorem, we can say that the absolute value of this function, or this sum from I equals 1 to n, f of ti times delta xi minus the Riemann integral from a to b for f dx. So this is less than epsilon. So, this is the absolute value if we are talking about the real numbers. All right. So if we're not talking about the real numbers, well, I don't know, because integrability is different in like different dimensions. So like for vector functions, and it's a little different, and I'm pretty sure it's different for complex numbers. So I think here we're assuming that all of our functions are real valued. I mean, I don't think that. I know it says it at the beginning of the chapter. So anyways, here we have this thing here. Okay, and we just established that this is actually this, right? Okay, so I can just replace it, right? And remember, epsilon is some arbitrary number. So I can say that f of b minus f of a minus the Riemann integral from a to b for f dx. Well, this is less than epsilon also, because they're the same. And if you have the sum, if you have the difference of two things, objects, are less than some arbitrary epsilon, I mean, it's because the epsilon is arbitrary, it means that these two things have to be equal. Okay, so I can write this. So since epsilon is arbitrary, any epsilon, then we have that f of b minus f of a is equal to the integral from a to b f dx. And that is it. Okay, so if there are any mistakes, or if you have any questions, if you want to know what the previous theorem is, let me know in the comments. I'm trying to build up my YouTube channel, so if this is helpful, you know what to do, like, subscribe, etc. And thank you very much. I hope this was helpful.